Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Thank you for joining us today under Miss Monday Technical Talk. I'm Asnor Juraiza binti Ishak from Universiti Putra, Malaysia. Before I introduce my title, I would like to share my area of interest. So as you can see, there's a few research that I currently do involved with the intelligent control system, modeling, simulation, control system, machine vision, pattern recognition, image signal processing, biomedical engineering, and also the rehabilitation assistive robotics. So the title for the talk today is that I would like to share with you is rehabilitation device design and development. This is the main topic that I will discuss with you. The first one is the rehabilitation device 1 is a lower limb associated robot, and the second one is a rehabilitation device 2, which is SEMG machine for ankle rehabilitations, and the third one is rehabilitation device 3 is knee rehabilitation device. Then the third one, which is a knee rehabilitation device, I will discuss generally because this project is ongoing research. This is the overall presentation outline. So today I will discuss on the lower limb rehabilitations, and next the lower limb rehabilitation, which involved two joints motions, and another one is one joint motions. Okay, for the two joints motions, it involved the knee and hip joints, where for the one joint motions I will discuss on ankle and knee. So that's why the design for the rehabilitation device involve two joints motions and one joint motions. Here is the introduction on the rehabilitations. So definition of rehabilitation, if according to WHO, okay, define rehabilitation as the combined and coordinated use of medical, social, educational, and vocational measures for training the individual to the highest level of functional ability. So that means the rehabilitation is a treatment designed to facilitate the process of recovering from injury, illness, or disease to as normal condition as possible. So here also I list several limitations of traditional manual therapies. So physical therapies and occupational therapies mainly depend on experience of therapists, and it is difficult to meet the requirements of high intensity and repetitive training due to the series of shortage of physiotherapists. The treatment cannot be granted. So as a result, the demand for advanced rehabilitation equipment is significantly increased, which will help patients to perform accurate, quantitative, and effective training. And then the application of rehabilitation robot can release the doctor from heavy training tasks, analyze the data of the robot during the training process, and evaluate the patient rehabilitation status. Okay, under this slide I will discuss on the lower limb rehabilitations. So as you know that humans have lower limb and also upper limb. So for today's discussion, I'm only focusing on the lower limb, which human lower limb is divided into three regions. Thigh located between the hip joint and knee joint, as you can see from your right figures. Leg between the knee joint and the ankle joint, and the third one is foot between distal to the ankle. So the example of lower limb rehabilitation can be divided into two exoskeletal robots and also the end effector robots. So the exoskeletal robot, the example that I can give here is Locomat, another one's LEX, and LOPS. So, and then under the end effector robot is vertical ankles and haptic walker. So now we move to the first rehabilitation device, which is a lower limb rehabilitation exoskeletal robot. This is the presentations outline for this device. The first one I will discuss with you all is objectives, and then general fabrication process, human gait, and then we move to the designs focusing for the actuation design and mechanical design. The last one is the controller. So this slide, okay, little bit explanation on the objectives and also the model that involved with the rehabilitation device 1. So the objective of this device is to develop a lower limb exoskeleton for rehabilitation, use pneumatic actuations based on force control, and then another one is to evaluate the VGRF of the exoskeleton user by using ground reaction force parameters. So this fabrication is the first prototype model, which involved 3 major parts, which are mechanical parts, electrical components, and software. Then, as you can see from the figures, okay, this prototype involved a lot of design, not only for the circuit design, but also the mechanical design. Before we design the mechanical, then we need to develop the modelings. So end up we will fabricate the device. And then we move to the human gait analysis. So the working performance of the exoskeleton is mainly determined by the gait phase. So the gait phase is widely used for gait trajectory generations, gait control, and gait evaluation on lower limb exoskeletons. And most of the performance of the lower limb rehabilitation robotic is analyzed by using electromyography, EMG, or gait observations. So the gait observations only provide information on kinematics, which is movement parameters, and then the EMG gait analysis lack of stabilities. So that's why we using the VGRF analysis is more suitable for gait analysis when kinetics of gait is considered due to able to show critical gait components and commonly used in the diagnosis of a typical gait, and also can be applied to analyze the patterns of mechanical loading of rehabilitation robotics use lower limbs. And as you can see, the figure from your right is the typical VGRF pattern for walkings. So so this is the pattern for the force patterns, force walking, and as you can see here, have 2 peaks, okay, 2 peak force for the normal walkings. So here we discuss on the actuation design. Lower limb rehabilitation exoskeleton robot need a mechanical structure matching human lower limb to realize force and energy transmission through the wearable connection. This can be achieved by designing the appropriate robot mechanism and actuations. So McKibben pneumatic artificial muscle is constructed of an inner tube surrounded by a nylon branded sleeve. Both ends of inner tube and sleeving are connected to custom design fitting that serve as compressed air closure and to transfer force generated to the system. To obtain a bi-directional rotative actuator system, Antagonist Configuration is used. So the Antagonist configurations, as you can see on your right side, the figure show. Okay, the first one is the McKibben pneumatic artificial muscle, and then the figures number 2 is the Antagonist configuration of the MPAM. Okay, here I will discuss on the mechanical designs for the Rehab device 1. So as you can see, the mathematical model on your right side, which divide into 2 because in this Rehab device 1 involved with 2 joints, which is knee joints and also the ankle joints. So that's why we need to do the calculations to find out the data for the ankle joint and knee joints. So after we satisfied with that knee joints motions and also the ankle joint motions, okay, then we can proceed with the our fabrications, which as you can see from the figures, the frames of the prototypes. So then we assemble it together with the air pressures and also the all the McKibben's pneumatic muscles. So the testing for these exoskeleton robots, using the treadmill, okay, to investigate the gait patterns, okay, and then from that we do the analysis from the gait patterns, which is based on the VG-RF. After we discuss on the actuation system and also the mechanical design, so now we move to the control of the lower limb exoskeletons. So for this lower limb exoskeleton robot, we use the simple type of control. So as you can see that several inputs and also outputs, okay, which involve the release and the air compressor, solenoid valve, and so on. So here we already discussed about the muscle that we design using the McKibben pneumatic artificial muscle. Okay, this slide I discuss on the Rehab device 1, lower limb rehabilitation exoskeleton, which is the improvement from the earliest device. So the improvement be done under the actuations. So the on the actuators. So where the first device we using pneumatic actuations. So for this one we using the electric motors. So design integration model for humanoid model and lower limb exoskeleton model with electric motor using PID controllers. So the first prototype, okay, using the simple control. So for this prototype, the second prototype, we are using the PID controllers. So as you can see that we designed the humanoid model and also the lower limb exoskeleton model. So after we design both of this one using the solid work, then we import it to the MATLAB using the C mechanics. So before that, the lower limb exoskeleton model we designed several types of lower limb executor model, as you can see there in the figures. So then after we do the simulations, okay, and we decide which is the suitable lower limb executor model, and then we integrate it these two models, okay, integrated both models. Then you can find you can see on the right side, okay, the model from the after we import it to the MATLAB using the C mechanic. So the improvement from the rehabilitation device 1, okay, we do the model, okay, for the humanoid and also the exoskeleton model, because we need to test the actuation system. So here we using the electric motors, which is a DC motor for the actuations. So here from this slide you can see that modeling and simulation of the standing up and sitting down maneuvers, okay, motions. So this one is only for the humanoid model, okay. So we can see that is a successful simulations. We get it from the these humanoid models, okay. After we import it to the MATLAB, we can see the gate analysis, okay. So here if you can see the joint orientation in standing up and sitting down motion, and then you compare it with the figures on the right sides, okay. Both graph, okay, the vertical force, okay, quite similar with the figures joint orientation in standing up and sitting down motions. And then after we design the model for the humanoid and also the lower limb exoskeletons, so we import it to the MATLAB using C mechanic. Then we need to sort, okay, we need to rearrange the block, okay. So end up we get it the lower limb exoskeleton model, which is the block on the upper one, and then the humanoid model block simulating is the below one. So it takes time, okay, to rearrange all the blocks, okay. Now we move to the rehabilitation device 2, which is SEMG machine for ankle rehabilitations. So here is the overall presentation outline for the device 2. The first one is the objective, then we move to the block diagram, circuit design, then the PCB design, and then the last one is the fabrications. So as you can see on your right side is the box, that is the SEMG machine that we created, okay. Then we use it for the ankle rehabilitation device. So to classify type of ankle joint motions, okay, we need involved with the several algorithms, so that we can get the type of motions for the ankle joints. So the objective for the rehabilitation device 2 is to design a low noise, affordable 4 channels Emg acquisition system for ankle rehabilitation. So why 4 channels? Because the ankle joint only involved with the 2 joint motions. And then the Emg data acquisition system consists of 5 main block surface Emg electrodes, preamplifiers, filters, amplifiers, and data acquisition card for analog to digital converters. The graphic user interface program known as LabVIEW was employed for displaying and storing the inquiry signal. Here, this slide will discuss on the circuit designs, which involve the instrumentation amplifiers, bandpass filters, and main amplifier. This is under the analog parts, where under the digital part are DEQ, okay, the conversions, and also the PC. So here is a slide discuss on the PCB designs and fabrications. So the figures, two figures on top is SEMG, okay, the electrode, and NIDEQ, okay, for the data acquisitions. Then on the left side, the figure on the left side is the PCB board for Emg amplifier PCB board, and then on your right side the casings of the Emg data acquisition system. Then several specification for these SEMG machines, okay, the gains, adjustable, and also the power supply, sampling frequencies 2000 as per second, and frequency bandwidth. Okay, these slides explain about the Emg Signal Assessment. The following table represents the Emg system channels configuration with respect to the leg muscles. So only 4 channels, okay, will measure 4 muscles, and then the ankle joint movement, okay, this ankle joint movement divide into 4 dorsiflexions, plantar flexions, adductions, and also the abductions. So this is assessment that we need to do based on the ankle joint movement. So this slide discuss on the rehab device trees, which is a knee rehabilitation device. Objective for this design is knee rehabilitation device using DC motors. Okay, this is because of the stage 2 of the rehab device 1. Okay, the actuation system improve it from the pneumatics to the DC motors. So we use the similar concept from the rehab device 1, then we implement it to the knee rehabilitation device, which only involve 1 joint instead of 2 joints from the device 1. So and then here we need also to model it, the knee device, okay, and also the humanoid device. After we get these 2 models, we integrate it, and then we do the simulations. So as you can see the figures on your right side, okay, the general overview of the projects, okay, because this project is still undergoing, so that's why I only can explain this part, even though that we already have that device, but still we need to do the testings. Okay, so development of knee rehabilitation device using Autodesk Inventors. Okay, so this is we design it, our device, and then export to the MATLAB. Okay, and from there we using the PID controllers, okay, to operate the knee rehabilitation device. And then there is PID being tuned, okay, so then we get the gains. So from that we can see we can gain the output, whether force or torques. Okay, so from that output, whether it's force or torques, we do the analysis. If the analysis achieve the standard gait patterns, okay, of the knee joint motions, then we can decide what type of DC motor that suitable for this knee rehabilitation device. Thank you everyone for listening my talk today.